So, today I was presenting on open agent safety, which was something we were targeting to like sort of build a more comprehensive framework for the evaluation of AI agents. Um, we see that AI agents are becoming more prevalent. They're getting introduced in a lot of high stakes settings, and it's pretty important to sort of faithfully capture these different settings they're being deployed in. Um, there is a lot of competitive pressure out there to like just deploy fast without like um, properly evaluating them in like say work settings or high stake settings. And many agentic systems that have therefore been released without like a thorough investigation into their failure modes. And this is something we're looking to like target with this work. Obviously, like agent safety is an area with like a lot of previous work. There've been a lot of good works targeting a lot of different failure modes. But where we feel existing benchmarks sort of lack is firstly the real world tools. So some works previously sort of try to simulate tools where these aren't tools that are like actually used by the agents in real deployments, and that leads to sort of a simulated setting where, for example, unlike a browsing tool which provides sort of real context, a lot of environmental feedback, these simulated tools sort of fail to capture the required context and required feedback that's required from these from real world tools. And another aspect is sort of the diverse intents. And the goal of these tasks in general is to sort of try to get the agent to perform some sort of uh, malicious behavior. And this can be done in one of two ways. So we can have the agent, like you can prompt it with something malicious, like which is malicious from the get-go, or it can be a sort of malicious behavior that's introduced over the course of the trajectory. Say the initial prompt is either underspecified or it's like ambiguous, and potentially there's a way to do it easily, but unsafely, or there's a safer way to do it, which is probably the one that should be chosen. And the user isn't trying to explicitly act malicious. And so that's why we have these sort of malicious and benign intents. And previous work sort of, not all previous work sort of capture that. And finally, we also want to have user interaction, which is the agent should be interacting with the user because users don't just give you the prompt and let you just complete the task. It's a lot of interaction involved. And this multi-turn intent tracking is something we also target with this work, where if you are being sort of socially manipulated, if you are being convinced by the user, how likely is the agent to sort of fail in these settings? This is what we again try to like focus on in this work. um so just getting to like how our framework works. So currently like we have 350 tasks focusing on multi-turn interactions, user intent, and real world tools. And this is what the agent sort of interacts with. This is the environment the agent sees. So the agent has access to like a file system. They can execute code and also perform browsing. um, on top of that, we've added like a new tool, which is to the existing LLM agent framework, which is chatting with like NPCs. And the goal of these NPCs is to introduce like a multi-actor component where where the agent is not just trying to satisfy the goals of one main like primary user, but also try to interact with these NPCs. And these can sometimes have different goals. And the NPCs can sometimes also introduce malicious goals, which the user didn't initially plan to. And as you can see from the example, a simple task like, okay, I want you to audit our company financials. And like another actor, like which is like an NPC in this setting, tries to introduce the malicious interference. And this is the sort of social manipulation settings that we also aim to target. And with like this sort of a framework, we try to capture like 8 different types of risks. And these risks we've collected from previous works, and try to aggregate how these map to existing existing agents. And like, for example, some of the categories like legal, financial loss, they were sort of easier to do with simulated tools because tools for those don't really exist these days. But we try to like map how these can actually manifest in current agent deployments. So first we can like sort of start with the task creation, which we like how we sort of get the three free tasks. And our goal is to consider the three aspects that we have, the risk factors, the intents, and the tools that we want to capture to sort of brainstorm, like we brainstorm around 80 seed tasks. And we want these tasks to be of like pretty high quality. So there's a lot of like yeah human involvement in this process. And once we have those C tasks, we sort of try to create different variants, different contexts, just to see like if the change in context can make the agent slip up. And also we have like sort of final evaluators and designing those evaluators and the full task framework for which again requires human intervention. So post the task creation, we have the task execution in the environment I just described. And for this, the agent that we use is OpenHands, which is pretty widely used like open source agent. And that actually like provides access to like these sort of tools, which we believe like sort of captures um, a realistic set of tools that general agent deployments have. And finally, the other important aspect is the evaluation. Um, we sort of try to target this from two axes. One is rule-based evaluations, which try to measure concrete, quantifiable changes to the environment. For example, file deletion, downloads, uploads. Like these are concrete changes in the environment state. These represent sort of harms that have manifested. The agent has successfully completed these tasks and made the malicious change to the environment. But there's also such second category, which where the agent might not complete the task, but that may be due to like capability issues, or yeah, that's usually due to capability issues. But the problem is that even in these trajectories, the agent agreed to do something malicious or unsafe. And we want to also capture these, which aren't manifested into the environment yet. And that's why we use an LLM as a judge to try to identify where in the trajectory did the agent like agree to some behavior or implicitly agree by like just performing the action. And these are the two dimensions that we use to capture them. And designing rule-based evaluators is a manual process. It's a bit slower. That's why if scalability is an issue, and for future extensions, researchers can even like use just the LLM as a judge as a good proxy for gender evaluation. And this is what an example looks like. So here we have this sort of benign intent. And this is what we mean when we say that the user can have pretty straightforward tasks where like, okay, you just need to like contact the customer and just a generic task about like, yeah, see what queries or like what questions does she have. And the agent, when the agent contacts the NPC introduces this intent in like the later steps of the trajectory. And this intent can sort of lead to because the user says that you need to like just yeah like whatever like requirements she has, like you need to like satisfy those. This malicious intent can sometimes act as because of the like the higher number of turns, the higher turn it's presenting itself at, it can sort of mislead the agent into being helpful just to satisfy the NPC's goals. But this is where we feel that there's a difference between direct malicious intent from the user versus from the NPC. And just looking at results and like how we try to compare the existing like state-of-the-art models, open source models, and reasoning models. And our general finding has been that yeah, the Claude models are generally much safer. They're much more careful about the sort of actions they perform. And as we can see here, we can see that reasoning models surprisingly are more prone to this sort of like unsafe behavior in the various settings. Here we're seeing how like user intent sort of influences this behavior. And yeah, like again, like O3 Mini and both DeepSeek R1 show pretty high unsafe rates. And what's also pretty surprising here is that the benign intent is pretty successful at so the initial user benign intent and later introducing the like some sort of malicious intent, or just having an unspecified benign intent, which where the agent can perform some sort of unsafe action during its trajectory because of the lack of specification, that sort of leads to pretty high unsafety like unsafe behavior rates compared to something like the malicious intent, where uh, some models, especially you can see like the DeepSeek V3 in Claude Sonnet 3.7, they're able to like their safety mechanisms get triggered and they're able to successfully complete the action without any sort of unsafe behavior. Um, but the problem with benign intent is usually because of agents prioritizing task completion over secure practices. And this is what I mean when I say that ambiguity can sort of cause higher unsafe behavior rates with benign intents. And and also we have like yeah, the we also see the models which are trained for to do like be more safe, sort of are trained only in the malicious setting, but we believe that there's a lower focus on how this when like malicious behavior like presents itself over the course of a trajectory. Say when we're starting with an initial benign intent, these models are not as capable in detecting these changes, and that's why it's a huge jump from their unsafe behavior rates in malicious and benign settings. Um, and that's why explicit cues are sort of what the models these agents rely on, and they may default to overcompliance in benign settings. And yeah, this is just presenting that where we see, like, especially for DeepSeek V3 and Claude Sonnet 3.7, there's a huge jump, almost 2x. And yeah. Um, and this, again, like this sort of, here the hidden intent, where here in this case, like previously looking at cases um, where we had, one second. Yeah, previously we were looking at cases where the benign intent was probably due to like underspecificity. But when we focus more on how the like if the initial user intent is benign, but the malicious intent is later introduced by the NPC, then we again see similar jumps, and that just shows that either you have overcompliance or you have uh, not adequate intent tracking across turns. That's leading to this rise in unsafe behavior rates. We also sort of look at the different axes, like, so here we're looking at how different risk categories like impact like moral behavior. And so for something like legal issues, privacy breaches of computer security, these involve authorization and like employer specific policies. And the tasks were designed such that these would be like apparent to a human and even apparent in like a singleton LLM setting. But when we're presenting these tasks to an agent, like in an agentic workflow, we find that these settings which require this sort of systemic understanding of what is right, what is wrong, what is authorization, these are the tasks where the agents are like consistently failing at. And for example, other categories like spreading malicious content or like generating or executing unsafe code, we identified that these categories are have received a lot of attention, and that's why they do see lower rates of unsafe behavior. And that's why, like, yeah, like a very well-tuned model like Claude Sonnet 3.7, it's sort of very cautious on these destructive actions because we're talking about like data loss means you're sort of performing like some sort of like data like deletion of files, or you're trying to execute like RMRF on your code and just yeah. So these sort of destructive actions is something that Claude has been trained to be careful about. And uh, and again, like yeah, heavy refusal training also helps with the decrease the spreading of malicious content. But the systemic policies, where policies are involved, that's where we see high failure rates. And another like what this work has allowed us to do is because this we have like a lot of tools available compared to previous works, we can analyze how different tools impact safety. And what we find is that browsing is like firstly, browsing has a lot of failure modes, and failure here refers to cases where the agent failed to even get to a state where we can analyze its safety. For example, I need you to download a file from the browser and then like make some modifications to it. And if the unsafe behavior falls in the modification part, then and if the agent sort of fails to download the file in the first place through browsing, that is counted as a failure, where it failed to reach a state which was safety critical. And we find that browsing is a tool that agents do struggle with. And we had like a realistic setting where we had pop-ups, we had a lot of navigation involved, multiple levels of like multiple clicks to get to where you need. And we found that this sort of led to obviously a higher failure rate. Agents can maybe, it's a capability issue in this area. But for file systems and code execution, we find that uh, this specifically refers to like when files or code files, they have content that is misrepresented by users sometimes, and the agent would often like agree to perform these actions without really looking at what's inside these files. And another aspect is that the messaging tool introduces a social manipulation risk, which, as I mentioned previously, when we're trying to balance the goals of multiple actors, then agents fail to like validate user roles before they either sharing sensitive information, they're performing actions on behalf of another, and so on. And yeah, again, in browsing, what we've seen basically with browsing is that because of the huge amount of context that each browsing observation adds, it leads to higher unsafe behavior rates. Um, yeah, because our hypothesis is that simply the browsing context overwhelms the agent and it sort of tries to just navigate the website and forgets about the actual safety practices that it should keep in mind. The general takeaways from our work has been that there is a general need for more realistic agent safety testing. And in this work, we sort of try to focus more on the work context. You have employees, you have employees with different goals, you have some employees who are trying to maybe just get done with their work early, and just yeah, like a more realistic setting in which these agents are deployed. And we try to capture these, but we also think there's room for more in this area, especially as like agents are being deployed in a lot of different contexts. And also, yeah, and that's leads me to the second point, that there's a lot of different deployment contexts involved with agents, and these strongly influence safety, because some areas we see there's a lot of refusal heavy training, um, or yeah, like some contexts have been previously covered in the agent training itself, but there are other contexts where there is not sufficient training yet. And also a big aspect of this is, as you discussed, the failure modes where, for example, the agent still struggles to use the browsing tool well. These systems and these frameworks that we design need to be extensible, because one, performance is increasing, and as we're covering more and more, as we're covering more and more like different applications of agents, then we need to also be able to incorporate these in the frameworks that we're developing. And yeah, this work sort of aims to address these to like some extent. And that's all I have. Thank you.
Thank you so much for the great talk. Any questions from anyone? Guess we have 5 to 10 minutes.
Yeah, thanks.
Mhm.
So, I wonder if while test those models, do you differentiate like reasoning models versus non-reasoning models? Like the
Yeah. One thing we noticed was uh, reasoning models were sort of um, over compliant. They would
Mhm.
they would sometimes even think of the like, okay, so performing this action would be incorrect, but over the course of like the reasoning traces, like at least with the DeepSeek R1, we noticed that over the course of the reasoning trace, like it sometimes just ignores that and again reverts back to like being helpful, that okay, still need to perform this task. So basically they reason the way out of a good solution sometimes. But yeah, like that was the general observation. They do try to be more helpful, and that's what's leading to, I feel, the increased unsafe behavior rates.
So you mean like reasoning model tend to be more compliant, like more
Yeah,
like
yeah.
safer?
Like even if they might think, so they might, like, for example, if I'm talking about say deletion of files, they might reason about it and say, okay, like this command may be harmful, it might delete some files, but then the subsequent reasoning sort of just ignores over that and like tries to like, okay, so to complete this task, I need to say do this step and then this step, and they sort of ignore their own reasoning about why this was harmful in the first place.
I see. Cool. That's very interesting to know. Thanks.
And you also mentioned that when the context is long, right, as in browsing case,
Yeah.
it's generally detrimental to safe behavior. Kind of the fact that the agent has to behave in a safe way is kind of lost in long context. Is that
Yeah.
some general observation, I would say, or is this something still specific to browsing, for example?
I feel browsing is like an extreme case of this because like we at least we like the trajectories we had, like browsing trajectories had like went up to say closer to 80, 90 turns compared to other trajectories which are 50, 40 turns. But
Mhm.
yeah, like I would say it is a general problem, and this also manifests sometimes in like a different form of this, where if you have multi-turn intent tracking, and so if it needs to perform say one action to get to like say the next like sort of malicious where the malicious content is being introduced, then if there's some sort of context which predates that, then and it sort of overwhelms the agents again safety behaviors, so that again like if you're seeing the malicious content at say step 30 instead of step 10,
Mm.
we're like our observations were that that sort of again that extra context overwhelms the agent, and it is more likely to comply and just perform the action.
Mhm, mhm. Sounds like yeah, I've been also personally trying to kind of jailbreak the models, and like jailbreaking only a simple example of that. And I've always been possible to jailbreak so far all the models. So it's fairly easy, and I think kind of increasing the context length is potentially one way to
Yeah.
kind of do. I started wondering whether we'll actually reach a point where we cannot actually do any we cannot induce any unsafe behavior.
Like one of the things I started seeing what we saw with Claude in this, and like also even with, like in the later iterations of Claude, it is it detects when it's being tested, and that leads to like if you, for
Yeah,
example,
that's true. Yeah.
yeah, like if you try to like prompt it, it explicitly says, so I think I'm being tested, and that's why I won't do this. So I don't know if
Mm-hmm.
this is bad training practices or yeah, like that's one way
Hmm.
models can start to avoid getting yeah like
Hmm.
preventing breaks.
But I think you also mentioned that if you pretend to be benign and hide your intent, then
Yeah,
these models are still not
yeah,
safe, right?
maybe like the also train on these like benign intents,
Mm.
but yeah, I think but that's why the benign setting is sort of difficult to fully address because it overlaps a lot with the underspecified setting, and general solutions in that are like difficult.
Underspecified, as in like a behavior may be okay in some other context, whereas in
Basically,
some context it's not.
this would stem from sorry, this would stem from so I have presented you with a task, but I have not presented like I have not explained like how you should do this.
Hmm.
So for example, if you're like say storing an API key in a code base and like it's a public code base, I just say that okay, you just need to implement this and this in an API key somewhere, but I haven't specified that oh, you should put it in the config.toml file, but the agent
Mm-hmm.
just hard codes it directly into the public code base. So these are the sort of like under specificity cases
Hmm.
which can lead to like harm.
Hmm.
These are not explicitly malicious, so that's why the benign intent.
Hmm. Hmm. Yeah, yeah. This is quite interesting. Then it brings us to this question of also the interface question, how expensive it is for human users to specify all the intents and
Yeah.
instructions. I guess I guess that becomes a little bit overwhelming at some point that you have to
Ye-
specify
like
everything.
yeah, maybe at some point we just need to, like, the foundation models themselves need to be trained on these
Mm.
better code practices, like higher quality data of the initial training, so that you don't eat, like, if you have some aspect which is underspecified, you are not trying to just find the easiest or the minimum steps to the solution. You're trying to actually focus on like the general better practice, like like as I mentioned, the policies aspect also is not well instilled, that if I ask you to, okay, so modify this file, but what is the authorization of the person who's asking you to modify this file? So this sort of policies based training, I think that is what is also lacking. So you don't need to
Mhm.
always like fully specify the instruction, but if these models had some sense of policies as part of their training or something, then they could yeah, maybe improve on that.
Mhm. Mhm. Um, if there's no other question from the anyone else, I also wish to ask you a little bit about the future outlook. Like, I was already kind of hinting at that, like, oh, maybe this is doomed to fail. But what do you think about the research itself? Um, where do you think the research in this domain is going, and what's probably worth looking into at this moment?
Like so, like in this work, we had like sort of two observations. So one is you are trying to maybe account for a lot more context. You want the framework, the benchmark or framework to be extensible, catch a lot of different settings. But what these different settings are leading to is that so the LLM judges we used in this evaluation, we actually extended this and we had sort of a human annotation study. And we found that with these sort of new, like if it's sort of multi-intent tracking or as I mentioned, long context, LLM judges are failing in this, like these sort of environments because they're not explicitly trained in these situations. And first, I feel like a key component is improving the LLM judges we have. So at least you're able to detect when things go wrong, and only then you can maybe try to like work on, yeah, like concretely, maybe you can identify what things we need to work on to like prevent these um, like unsafe behavior practices in the first place. So I think detection currently and like evaluation, that's maybe
Mhm.
the first step, and then it would be sort of more interesting that how can we sort of once we have the evaluation figured out, how can we convert that to say if you're using existing paradigms like
Mhm.
sort of an
Mhm.
RLPR task which we can optimize the model for. But yeah, I feel
Mhm. Mhm.
evaluation currently is um, area which is majorly lacking.
Makes sense. Okay, I have some follow-up questions, but for the interest of time, I guess we have to move on to the second speaker.
Yeah.
So,
Uh, yeah, so yeah, I would love to introduce Dr. Hawan Wang, who is an assistant professor at UIUC. His main uh, work has been on trustworthy, like he's part of the trustworthy machine learning initiative, and he's been working on developing and understanding trustworthy machine learning methods, and with the focus on biological and medical problems. Um, I'll give it over to Dr. Hawan.
Thank you. Let me share my screen. So I made a very cool opening slide. So yeah,
just for this talk?
yes, yes.
Oh, wow, okay.
Yeah, actually, I don't know the exact format of this talk. So the first half is more like a reading group, very basic stuff, and the second half will be the some recent research we did in our team. Okay. Yeah. So yeah. So yeah, thanks for having me here. And today we will share a bit on this large language model based data science agent. So let's first motivate it a bit, like the success of these large language models and has well prepared us to build AI to automate the data science process. For example, it has like a massive knowledge built in, and also it's can do very efficient in data analysis. Like it's basically more efficient than what the human can do. And also, although this is still in question, but nowadays we have seen more and more capabilities of large language model writing decent code, and also last but not least, it's very easy for this large language model, for these AI solutions to scale to massive data. So we are quickly welcoming a new era where these large language models will serve as this main force to do data science analysis. And so the first thing we can try is probably using some prompts to do this data science. Like we create some prompts to select data sets, ask the model to pre-process data to do data analysis. And however, this will quickly overwhelm large language model. And then a very natural follow-up is like just create a team. And so nowadays known as the multi-agent system. So build upon this background, we conduct a survey on this agentic AI data scientist. And also here is like in the survey, we offered mainly two perspectives. Like one is from the more AI and engineering perspective. We talk about how to build these agents. And then the second one later, we will talk about like what tasks we build these agents to solve. So here is a summary for the first part, like from the agent perspective, that usually when we build this multi-agent system, like we start from selecting these agent roles, and then we decide those execution structure. And sometimes we need some external knowledge, and finally we also need to decide some reflection mechanism. And so starting from the first part, like agent role, like our survey kind of categorized them into different categories. Like for example, we start with the single agent where it's basically the same as we interact with a single large language model. And then like for it to be considered as a multi-agent, like we have the regime where involve two large language models, and then we can say like the value of survey start to emerge. Like although there are many papers on that, essentially they fall into these two main categories. One is like they work in a chain, like with a very dominant structure is like one agent responsible to make some plans about guiding the other agent how to do the task. And another regime that is extremely popular in multi-agent system is that these two large language models work in a pair. Like one of them performing some tasks and the other like try to evaluate these tasks so that together they try to do this job better. And one of the most popular example in this is like one agent write the code and the other review the code. And then things get a little bit more complicated when we have multi-agent system where we build many large language model together to solve one task. And in this, like uh, but this essentially it's just the two agent system grow bigger. But we also observe like different ways to construct it. For example, like one thing about the roles is sometimes it's usually assigned with prior knowledge, and with the most popular example of software engineering, like most of those software engineering multi-agent systems are designed by following the actual process of software engineer. Like we have those project manager, we have those architect, we have coders, we have reviewers. And later, people might find that it's still a little bit too much for the large language models, especially back then when the multi-agent system just got popular. Like 2 years ago, the coding ability of those large language models are still yet to be improved. So a solution to that is like we try to find out some minimum functions so that the large language model could start to work on that. And also, other than that, there is also another very emerging structure is like we have those one centralized agent tries to control and assign the tasks to other agents. And building upon that, nowadays, like the agentic AI grows more, grows to the direction that more dynamically. And so nowadays, many of the works do not talk about a fixed pipeline of agentic structure, but instead it's usually like the agent can grow their own structure along solving the task. And one way to do that is this kind of hierarchical agent generation, like we have one controller overall, and then every time it assigns task, split the task, it assigns to new agents following it under this task, further split the task and assigned to the agents. And another very representative way of solving it is like we build some iterative agents that can generate the agent structure through some feedbacks. For example, like we start from some agent workflow, and then along the way to solving the tasks, the agent will figure it out themselves. Like some of the part are not working that well, so they start to change that agentic structures. So basically, some quick summary of this first part about agent role is like uh, usually it falls into these dimensions. And one thing that we noticed along with working on this array is like, although the field is start with some fixed designed agent structure and roles, it's quickly move along the direction that to the more dynamic construction of the structures, that usually it is the job to the agent who design what the best structure or roles for solving their tasks. So that's for the role design. And uh, uh, building upon that, we also look into the execution structure of how this multi-agent system. And is like at a very high level, it falls into these two categories, like whether it's a fixed step-by-step pipeline or like the agent decides dynamically. And of course, whenever it can fall into two categories, we can ask a third question. We can ask a question like, what if we just mix these two? So so of course there could be that hybrid approach. And here is a little bit more details about the execution pipeline. And but since this is usually tied pretty close with the role design of the agentic structures, then I think we can skip the details here. And also together with the execution of people also like work on different routing strategies about how to assign those tasks to different agents. And similarly, like when the agents need to, or when the people who work on the agent system or the agent itself want to design want to decide the architecture, they also need to figure out a more systematic way to split the assigned task into smaller tasks so that it can be assigned to different agents. And again, like we can split the tasks in two major ways. One is like based on the basically compose the tasks into different layers, like the big problem and then those smaller problem. Or like more, or in another way is like we directly chunk the problem into multiple steps, and then each agent can take one step. And again, of course, whenever there are multiple ways, we can ask the question like, how about we mix them? So yeah, uh, and also the takeaway is kind of like a fairly given structure based on the summary, like the vertical structure, like usually about going deep into the question. So it's usually improves upon like for the more complicated problem. And the horizontal structure is more like trying to solve the problems in parallel. So of course it gets quicker, but it won't offer us some deeper capacity in solving those problems. Okay, and so similarly, like one thing we notice along summarizing all this is like we notice the again like the agentic AI research start from some fixed route, like fixed design, and then quickly evolving to an area where the agentic architecture needs to evolve themselves based on the task. And we believe at this moment it's still like the evolving agent is one of the major direction to go. And following that, some other parts are quite straightforward. For example, how does the agent get external knowledges? Like usually these fairly basic ways, and also how does that how do those agents get feedbacks? Like also we put them in these categories, but as you can see on the slides, that essentially they are from the uh, same structure. Like it's about just about where to get information. Either we get information from other agents, or we get information from some external tools, and we get information from a human. Like maybe to an agent like a human is also a tool to offer feedback. So, then in our survey that we also talk a little bit on the data science perspective, like how these data science are usually conducted so that we could further decompose this to build multi-agent system. So that's the first half of this talk that I think is more on the basics about constructing a multi-agent system that hopefully that serves some of our purpose as a like a reading group. And then for the next part, we will share a little bit on our recent research about automating bioinformatics tasks. And so one way to motivate the task is like we usually talk about like when we conduct the bioinformatics, it has a fairly significant value. And actually the the thing that motivates us to do is like the invention of a tool called MamaPrint, that it is simple to diagnose breast cancer, and it's currently like a business of I believe hundreds of millions of dollars. And however, from the very beginning, it starts with around 10 bioinformaticians to do some analysis on some breast cancer gene expression data and identify like around I think a couple or tens of markers that serves as those genes that are predictive of breast cancer. And then they later develop that into a tool that currently nowadays helps is helping like millions of women across the world. So we asked the question like, if we conduct bioinformatics on one data set, it has this much power, how about we repeat it for all the data sets we have? And with that, we motivate this study, like we want to build some agentic AI that can help us to repeat this process like relentlessly across all data sets we can find. And so following that motivation that we built our first system, like back then when we do it around 2 years ago, we call it team of AI made scientists. And now as the multi-agent world becomes more and more popular, we kind of following the trend called genomass, like geno multi-agent system that essentially is still the same design rationale as we have a couple years back, where we have the large language model serve as project manager, whose main job is to understand what the user wants. For example, like what are the genes associated with this cancer when we considering like their vitamin D intakes. And then the project manager will analyze this question and then assign different roles, including like one of the major roles, this data engineer, that his main job is to find the raw data and process those raw data, and which sounds like a simple task, but actually to a large language model agent this is one of the most challenging part of our system, because like in real world, the raw data can come in different formats with different explanations and sometimes even different meanings. So the data engineer need to be able to navigate all these complexities then to do the job. And that's why like we're also allowed to interact with another large language models who is specially designed as domain expert, just to offer them those biology contexts, like what are those key terms mean. And then after the data engineer process the data, it will pass the information to the statistician agent, and who will conduct all the statistical analysis. And this part looks very complicated, but it's usually some predetermined steps. And the agent only need to select like which path it needs to go based on its own understanding of the data. And then after analysis, it can report the results. And along the way, since these two agents also needs to write code, we also introduce that very basic two agent structure. Like whenever there's an agent to need to write code, we assign a reviewer to help us write better code. And also along the trajectory when we build this, we also introduce some very interesting, notice some very interesting stuff. Like for example, this code reviewer sometimes is never happy with the code these guys write. Even like when this code already passed all those basic requirements, it will keep telling that, oh, okay, it looks good, but you can make the code write more efficient, kind of thing. So later we decide that when we build this, we try to limit like how many conversations they have after the code reviewer is unhappy with certain rounds of revisions, then we will let the code pass. And to evaluate it, we also introduce a genotext benchmark where we collect like real world research questions and we actually collect these questions and we manually go through all this process, including like checking the quality and following those basic steps like bioinformatician will usually do. And then we manually run the machine learning models, find the results. And so that we create like more than 1,000 records of these research questions with the genes we can find from a bioinformatician manner, so that we can later use this benchmark to evaluate like whether our large language model bioinformatician agents can do as well as human bioinformatician can do. So with this benchmark, so there is a little bit more information about the benchmark. And with this benchmark, we evaluate our system, and we also iterate like several versions of it from the Geno agent, and then later we get it improved to this what we call it GenoMass nowadays. And here we can say like it's we basically gradually granted the performance to more human level, human in parallel level performance. And here we can say like even for human experts, they do not always agree with each other. And hopefully the large language model can soon achieve that level. So, and also, this is a more recent work about to answer the question like, what's the big deal that we can have some multi-agent system to automate the data analysis? Because like when we do this, we often get the questions like, hey, are you trying to get my job kind of thing? So, but however, we want to say that we believe the significance of multi-agent system, especially this multi-agent data science agent, multi-agent data science system, their job is not just to their goal is not to replace the human efforts, but to perform the tedious tasks repeatedly. For example, in this work, we ask those agents to repeatedly conduct the analysis over 1,000 disease with conditions. Like this is a job that I don't think any human bioinformatician will be interested to do, like for many reasons actually. And however, an agent can relentlessly perform this task and analyze repeatedly over 1,000 disease and find different genes. And then the significance comes in like when we have this many results, we can ask the question like, what are those similarities of these diseases in a way that we previously overlooked? For example, previously when we talk about like there are some similarities of those diseases, we also talk about it like from a symptom level. Like for example, like someone has a flu might similar to someone has some mild COVID, and then maybe there are some relationships between these two diseases. But on the other hand, nowadays, it allows us to ask the question like, what's the relationship, what's the similarity of diseases if we look at the molecular level, if we look at the transcriptomic level, like what are the underlying structure that making connected to disease. This will open new doors about solving this problem in a new perspective. Okay. So this is our construction of the agents following the bioinformatics pipeline. And building upon that, we also get some questions occasionally like, okay, so now you guys can do the agents to simulate a bioinformatics pipeline, but sometimes we need agents more than that, right? What if we don't really know what the pipeline is? So that motivates us to build this work that we want to do some automated data science agent that can work on any domains, even when we don't really have that prior knowledge. So this is motivated by basically two types of this multi-agent system. Like sometimes, like one track of them is like some general purpose system. They are very flexible but struggled with specialized tasks. And the other is this task-oriented system. Like they are very strong at predefined tasks, but they cannot they cannot adapt to other tasks. So basically, we want to try to solve this issue. And basically, the motivating question is like, can we design a system that the system can design itself based on the task? So with that in mind, that we build this system that back then
So maybe a quick time check, sorry.
Yeah, sure. There are
Yeah.
only a couple slides. So we build this
Mhm.
prompter and we compare it to systems like from general purpose and from very specialized ones. And as we can see, like even we compared with specialized agents, we can beat like their improve upon their specialized agents sometimes. Like these are like the best work on each of those domains. Okay. And also we introduced this tool with a UI that if you go to this link, you can see like the tool with a UI that allows anyone without AI or machine learning expertise to use the system. I think that's it. Yeah, thank you very much.
Thank you so much. We actually have time for some questions, so please go ahead if you have any.
Yeah, I had a question. I think earlier in the slides you mentioned something about like the vertical hierarchy and the horizontal hierarchy. I was wondering, yeah, like based on your findings or like your survey, um, if you found that there was some problem with the how context was managed, like so if in a vertical hierarchy, how the main orchestrator sends it to the subagents, and do you think there's a best practice related to this?
Uh, Sorry, I'm not sure I got the question.
No, like so for example, sorry, like what I mean is, so given a task description, like you have like a
Mm.
full input from the user. So how does one agent communicate like what is relevant to like a sub agent, and how like is this information transfer a bottleneck from like your findings?
Mm, well, that's a great question. At this moment, like I've seen more than 99% of the work, these agents talk with each other through natural languages, right? It's like one agent's output in natural language serves as the prompt of the other agent. And then I think nowadays people are start questioning that, whether that's necessary. Uh, and on the other hand, we do notice that sometimes the output of one agent is not necessarily serve as a good prompts for the other agent because like it focuses too much on solving its own task. And so we actually have to uh, prompt the first agent to write proper prompts for the second agent, if that
Okay.
makes sense. Yeah.
Yeah, that makes sense. Yeah, I was more curious about like, especially in the horizontal setting, if because if they're parallelly executing these tasks, uh, is there sort of some information transfer there? But yeah,
Oh, I think that's more depend on the nature of the task.
okay,
So if it's parallel, it's like the task is like can be separate to begin with. So they don't
okay,
need to communicate with each other. Yeah.
that makes sense. Yeah, thank you.
Okay, cool. Thanks.
Thank you so much. So now it's actually time to kind of switch, but I wish to thank the speakers again, Han and Sanidya, for
Sure.
presenting great work and answering questions. By the way, there's one question from Cornelius in chat. I saw that Anitya, you answered the first question, so presumably you can also see the second question. And it'd be great if you can answer the question as well. In general, we have Slack channel, so we can continue the chat and Q&A in the Slack channel if you wish. So that's another way to kind of continue the conversation.
Yeah. Also, some questions are for me. Like, sure, I can type in later, and if I'm interested, feel free to drop me an email.
Yeah, there are different channels. So thank you again for the speakers. And we move on to medical AI section now.